There we go. All right. So yesterday, your number one looked like this, and we were a little concerned about some of these number one problems because they did not look as scattered and as random as we would like them to. So I first want to talk to you about your problem yesterday on this number one and kind of talk to you about through some of the thinking process that you do if it's not as good as you would like it to be scattered. So here we go. So on this number one yesterday, we were fine. We put in our L1, L2. We did that fine. We were all good. And we came over here and we did our residual plot, and you know what? Because of the lesson, it had a nice, down-up pattern, and so we were good in saying, yes, there is a pattern in the residual plot, therefore a linear model is not appropriate. Okay, so we were fine with that. Now, here's where it kind of got tricky. We ended up having this one here look very much like the one above, so quite a few people were a little concerned because, yeah, it's typically not supposed to look the same as above when you log the y's. And I'm not exactly sure why it was so close, but I would imagine that this y scale was very different. But otherwise, it looked pretty much about the same. It was a little different because we got a different residual plot. So when we looked at this residual plot, unfortunately, we were not liking that it almost kind of looked like we had another pattern going on. So let's address that. So in summary, we had to find that one of these two options was better than the other. So here's the process that we went through on this. We first compared the two. This one is definitely clearly, a down up. This one is maybe a little more varied or a little more volatile because it's down up, so it's definitely doing some more motion. Furthermore, this one had an R value of negative 0.96, and this one's R value is negative 0.98. Now, you cannot go just by the R values, by the way. But that, in combination that this one had much more movement to it and is maybe considered a little more scattered, then I say, because it's more scattered than the above and the R value is stronger, an exponential is better. Now, I'm not saying it's great, but of the two, I would go with this one, okay? So that's what happens. If you end up with a situation where you can't really tell, then do that kind of comparison to see which one is better. Now, let's talk about what we're going to be doing today. So here we go. When we ended yesterday, you guys got equations such as this right here. You got that the predicted log number of swings is equal to this based on the length of the pendulum. So, if I said, I've got this one particular grandfather clock make that I'm putting on the wall, I don't know, something that I've got say I have a 15-inch pendulum that is hanging down there from the clockworks, and I want to see what number of swings we got going on. Well, I asked to predict the number of swings. What would this equation give me? Predict for me. The log number of swings. I am not interested in the log number of swings. I want to know the predicted number of swings. That's what we're talking about today. How to, in a sense, undo this log so that you can get it back to the predicting of the number of swings, not the predicting of the log number of swings. So, look at your paper you picked up today. You picked up this assignment right here. And we're going to start up here. So, here's what the deal is. We just said we cannot leave our equations from yesterday in the predicted log y form. Because who cares about the predicted log y? Do you go around saying, oh, the predicted log number of swings or the predicted log whatever? No. We want to know about the predicted y value, not the predicted log of y. So therefore, we are going to have to transform this from log y back into y by, in a sense, undoing the log. Here we go. Since this was an exponential transformation of condensing that y, then we know we're going to end up in the exponential parent function form. So this is the exponential form, where you have the predicted y equals this a value. This a value is derived from the y-intercept in that equation that you found yesterday. And this base of the exponent is derived from the slope in the equations that you found yesterday. Now, the reason that this is an exponential equation is because the variable, the x value, is in the exponent. So that is what is the nature of making this thing an exponential equation. So, let's talk about how you do that. You're going to end up setting log y equal to this number that you got yesterday here. Log a, sorry. You're going to set log b equal to this number you got here. You're going to mathematically undo those numbers to get the plane A and the plane B. So let's do that with the equation from our notes yesterday. You don't have to get out those notes, but here's how we ended yesterday. When we had the chip problem, we were talking about the frying time. Remember yesterday we were talking about the fry time, and we were trying to predict the moisture content. All right, here's how that problem ended at the end of yesterday's notes. We came up with this. The predicted log of moisture content, the predicted log of moisture content was 1.167 minus 0.01889 times fry time. Is it going to make sense for somebody to say, oh, the predicted log of moisture content? No. We want to predict the moisture content, so we need to undo this, and here's how we mathematically do that. The a value is going to be derived from this y-intercept value of that equation. I'm going to come over here and undo the log. So I say, let log of a equal 1.167, and to undo this log, you rearrange it exponentially. What is the understood base for a log? 10. So the way I get out of this log is by going 10 to the 1.167 exponent equals a. And then you can go and do that computation in your calculator here. And you can see my top line, 10 to the, so you have the caret button, 1.167, and that comes out to be 14.69. So the a value is 14.69. That's going to be this value right there in the exponential equation. All right, let's do the b part. So I'm going to set this slope equal to log b, and then I am going to unlog it. So I'm going to go log b equals negative 0.01899, and I'm going to undo the logarithm and make it exponential. 10 to the negative 0.01899 power equals b. So I have to put that in my calculator, and I get 0.957. So the value of b is 0.957. And these are the numbers that are in this exponent form. So in summary, the final equation that is done is this. Predicted moisture content. See, it's not log moisture content anymore. I have undone the logs of this problem. Predicted moisture content equals the a value, which is 14.69, times the b value, which is 0.957, to the exponent, which is the fry time. Done. Now, I want to relate this, I want to tell you what this actually has done for us. Sure. So I want to tell you what getting that equation has now actually done for us. Here it is. I still have my chip problem information in my list. So in my L1 and L2, I still have the chip problem data from yesterday. So guess what? If I come up here and I type this exponential equation into y equals, because I want to look at it and see how well it fits my L1 and L2. That's what I have found, is the equation that fits my L1 and L2 by going through this whole process. So I put it in here, 14.69 times 0.957, or 0.957 to the x power, and watch, here we go. I'm going to graph or plot the original L1 and L2, which was curved. But I have come up with the equation that fits that curve, and here it goes. Okay, so that's what happened. We had the original L1, L2 that wasn't linear. We condensed it, made it linear, found the equation that fit it linearly, and then undid that back to this curved equation in exponential form that fits the original data. So now you are going to take yesterday's assignment, and yesterday you were leaving off all of these bottom sections of each page. So number 1, you stopped and you didn't do this bottom section. Number 2, you stopped and you did not do this bottom section. Now how about number 3? Remember number 3 was beautiful. It had nice scatter. It was linear. So did you even go forward with that? No. But our number 4 was better in an exponential model. So I want you right now to first undo all of those logs and put them in their exponential form. And then your assignment for today is this here. You have 3 problems. Now I want to tell you real quickly a couple of things about that. So will you get this, will you open this homework up? Let me kind of give you a couple heads up of some problems I've noticed throughout the day. Here we go. This is the second page of what you picked up today. Yes. This is problem number 1 about the number of transistors in the year. Okay. So here we go. Please, before you start, notice that I have defined for you what I want your x values to be. So here I say, for years, use the number of years past 1970. So you're going to be using 1, 2, 4, 8, 12, 15, and so on. Okay? I also did that here on number 2. I said, use the years past 1980. Well, a problem still happens because the 1980 is how much past 1980? It's 0. Okay. The problem occurs when you go try to make your L3. What do we normally put in L3? We normally put the log of L1. Okay, we would normally put the log of this x data into L3. You know what? You cannot log a 0. If you try to log a 0, here's what a log of 0 means. 10 to the what power equals 0. Can you think of something that the power that makes 10 a 0? And it's not 0. 10 to the 0 power is 1. I'm not going to do that little proof for you. But there's nothing. That is why if you tried to do your L3 on this problem, you would get a domain error because you cannot compute the log for 0. So we don't need the L3s. I just had you kind of put that in as a habit because we will use them tomorrow. So don't put your L3 in on this page. Do not put your L3 in on this page. Number 3 has the same problem. Do you see that there is a 0 in the domain? If there's a 0 in the domain, then you can't log 0. So do not do L3 on this problem either. You don't need it. Done. Okay, so I want you guys working on that. I'm going to come around and stamp you for last night's homework while you are working on that.